video, we're going to be taking a look at estimating p in the binomial distribution. Basically, the idea here is that rather than estimating a mean mu, we want to estimate p, which is the population proportion of successes. And you see this a lot in polling data. This would be how we estimate proportions of people who are going to vote for or against something, or the proportion of individuals who favor a certain political candidate. This is typically how that's done. And this is why you'll see in public opinion polls, there'll be an estimated percentage of people who, like I said, are going to vote for something or who agree with a candidate, and then there'll be that plus or minus a certain amount of percentage points, like plus or minus 5 or plus or minus 2. That's where this comes from, is the margin of error associated with estimating p. Now remember here that successes are just the things that we're interested in. These may or may not be positive outcomes, but they are indicative of what it is that we're interested in studying. So whatever it is that the question is asking about, estimate the population proportion of blah. Whatever that blah is, that is defined as a success, even if it is a negative outcome. So let's take a look at, again, the conditions. There are conditions for inference associated with this as well. The first one that you'll find holds true for every single confidence interval that we want to compute is we need to have a simple random sample. The data need to have been randomly sampled. If it's a biased sample to begin with, we have no business using it to estimate the value of a population parameter. Okay, so we need a simple random sample. And then because estimating p is based on the normal approximation to the binomial that we took a look at in the sampling distributions chapter, there were those conditions that NP and NQ had to both be greater than 5 in order to be reasonably sure that the p-hat distribution would be approximately normal. It's exactly the same here. NP has to be greater than 5 and NQ has to be greater than 5. Here's the issue though. The condition for inference literally says NP and NQ, but the problem is we are estimating p. We don't actually know this value, therefore we don't know this value either. So what we tend to do is if NP hat and NQ hat are both greater than 5, we take that as reason enough to believe that NP and NQ are probably greater than 5. Okay, now remember here, P and Q are the population proportion of successes and the population proportion of failures. So that means that p hat is the sample proportion of successes. And q hat is the sample proportion of failures. Okay, so we're taking the sample size, multiplying it by the sample proportion of successes, and what that gives us, what NP hat actually gives us, is the number of successes in the sample. Similarly, if I take the sample size, multiply it by the proportion of failures, what that will give me is the number of failures in the sample. So as long as I have more than 5 successes and more than 5 failures in my sample, I can be reasonably assured that my p-hat distribution will be roughly normal, and therefore I can use the methods that we're going to talk about in this video to calculate the estimate for p. Okay, so that's what I need to check. I need a simple random sample. I need more than 5 successes and more than 5 failures in the sample. And notice that this is an and. Okay, this is not an or. And these are also not greater than or equal to. They have to be strictly greater than. Okay, so that's what we're looking at here. Now, if we were going to do this by hand, again, just like everything we've looked at, there's a formula for doing this by hand. And unsurprisingly, we'd start with p hat as our best guess or our point estimate for p. Since we're trying to estimate the population proportion of successes, our best estimate for that is our sample proportion of successes. And then we add and subtract a margin of error. Okay. And the way that we calculate margin of error when we're talking about this particular distribution, the formula for that, if you're going to do it by hand, is p hat plus or minus z sub c, since it's based on the normal distribution, we're back to that critical z value, times the square root of pq over n. Oh, sorry, p hat q hat over n, because obviously we don't have p and q. So that should be a p hat and a q hat. Okay, there we go. So this is what you would do if you were going to do it by hand. You're welcome to give that a shot. It's pretty straightforward. You're just plugging in values. This, remember, you get from the table in the book. And then all of these values would be given as part of the problem. Or you can use the calculator. Or, again, all statistical software packages will have the ability to do this as well. In the calculator, the thing that we're going to be using is called one prop z int, and it stands for single proportion z interval. So just to recap, when we wanted to estimate mu and we had a single sample, if sigma was known, we used z interval. If sigma was unknown, we used t interval. But now we're switching from estimating mu to estimating a proportion. So in the calculator, that's one prop. And proportions are always based on the z. There's never a choice between a z and a t if you're estimating proportions. Okay, so this is the thing that we're going to use. So you would start, just like before, by checking your conditions for inference, making sure they're satisfied, putting everything into the calculator, getting your interval out, and then interpreting that interval. So let's take a look at an example where we do that. Here we have, let's see, case studies showed that out of 10,000, let's see, 10,351 convicts who escaped from U.S. prisons, oops, sorry, totally misspelled prisons there. There we go. 10,351 convicts who escaped from U.S. prisons. Only 7,867 were recaptured. Okay, so there's the data that we have. And we want to find and interpret a 99% confidence interval for the proportion of all escaped convicts who will eventually be recaptured. Okay, so there's what we want to do. First, we need to check our conditions. Again, we need a simple random sample, and we need more than 5 successes and failures in the sample. And this is to satisfy that NP greater than 5 and NQ greater than 5 criterion. Okay, so it doesn't actually say in here that I have a random sample. It just said that they were case studies. So for now, I'm going to assume that these were sampled randomly. If these case studies were not selected randomly, what we're about to do actually is completely inappropriate. The whole purpose of creating this kind of confidence interval is predicated on the notion that these conditions are met. Okay, so for now I'm going to take this as assumed. But if for some reason we were able to show or had reason to suspect that this was a biased sample, we would not want to proceed with our computations. Then we're looking for, were there more than 5 successes and failures in the sample? Notice that we're calling a recapture a success. So in our sample, there were 7,867 successes, right? Because that's how many recaptures there were. And that's in a sample size of 10,351. So how many failures were there? Well, there's a little bit less than 3,000 failures. So that's certainly greater than 5, right? Both of these are definitely greater than 5. You'll find that usually with sample sizes this large, if you're talking triple digits and above, it would be very, very rare for this to not be met. Okay, so we're taking this as assumed, so we're going to assume that it's met. This one is definitely met. Okay. So we're going to go ahead then and proceed with, in our calculator, calculating the, again, one prop z int is what this is called. Single proportion z interval. So when you go into your calculator here, we want to go to Stat, all the way to the right to Tests, and you're going to be scrolling down for a bit. Don't inadvertently hit one prop z test, because that does something different. Okay, so keep going down, z interval, t interval, 2samp z, 2samp t. There it is, one prop z int. Okay, way down there. So select that. Then here's what your calculator is asking you for. Where your calculator says x, it's wanting the number of successes in the sample. And we had 7,867. Then where it says lowercase n, it's wanting the sample size. So we had 10,351. Next to C level, it wants our confidence level, 0.99, because we were doing a 99% confidence interval, and then we calculate. And there's our values. It gives you your interval here. It also recaps what your p hat was. In our sample, we had about a 76% recapture rate. That was our p hat. And then it also reiterates your sample size. Here it was 10,351. So when we did our one prop z int, we got 0.74921 to 0.77084. That was the interval that we obtained. And then what does that interval mean when we do the interpretation piece? Start out with our statement of confidence. We are 99% confident that. What was it that we estimated? We were trying to estimate the proportion of all escaped convicts who will eventually be recaptured. So we are 99% confident that the proportion of all escaped convicts who will eventually be recaptured and then the last thing that we're supposed to put, we've got our confidence statement, then we've got what did we estimate, then we want to talk about what we found, is between approximately, and remember that because we're dealing with proportions, these are actually decimals representing percentages. So it's between approximately 75%, since this is 0.749, we'll round up, and 77%. Okay, we are 99% confident that the proportion of all escaped convicts who will eventually be recaptured is between approximately 75% and 77%. Again, that is assuming that this data was coming from a simple random sample. If it was not, then none of this math that we did would actually justify that conclusion. Okay.